a few people, in particular Gerald, so he will tell us about highlights of this.
Yes. The Resurgence program, I'm fortunate that Tin and Mithat already gave some details of the physical applications of this. Many different topics, unfortunately because of time not too deeply, but we can discuss more details later. And
Just checking my phone, sorry.
good, so that wasn't recorded, no. Okay. And if you're interested in more details, they gave some lectures at the winter school at CERN last year and at Schladming this year. These are very elementary lectures designed for students, so if you're curious. So some of the original physical motivation here was to try and do asymptotics in an improved sense in quantum field theory and more general quantum problems. It turns out mathematically there are some developments recently. It's hard to believe, but in the old topic of asymptotics, there are better ways to do it these days. And some of the physical motivation that Mithat and I had originally was to try and understand this infrared renormalon puzzle, which he discussed the other day. I'll say some more about that. And also some issues to do with non-perturbative physics in general, not just about instantons. But underlying this, there's a bigger picture. There's a more ambitious thing going on, which is to try and really give a non-perturbative definition of field theory through the path integral in the continuum, not necessarily through the lattice. And of course, to understand how it matches to the lattice. And this, of course, is not easy. It's ambitious, but it's one of my motivations. Related to that is the question, can we actually make sense of this idea of analytic continuation of path integrals? And again, several people have mentioned that in the conference so far. It's a very, very difficult problem. It's not a problem just for physics. This is a well-known problem to mathematicians, to chemists, to biologists. It's just a problem. Can we contribute something new to this problem? If you could, all of a sudden, many things that were impossible become possible. Path integral access to real-time dynamics, to non-equilibrium physics. That, in turn, tells you how difficult a problem it is. Okay? Mathematical motivation. I'll tell you where the strange name Resurgence comes from. It's a relatively new idea in mathematics on the timescale of mathematics. The name comes from some work by a French mathematician, Jean Écart, from 1980. But you can trace the ideas all the way back to Stokes. Stokes was trying to understand rainbows in a very deep sense. And he was, in particular, in modern language, trying to understand the asymptotics of something like the Airy function. And he really understood something very, very deep about asymptotics. At a broad level, the idea behind Resurgence is to try and do what we would call perturbation theory and what we would call non-perturbative physics together, not separately, not in different chapters of a textbook, not on different pieces of paper, on the same piece of paper. And the question is, do you gain anything from that? So we all know that perturbation theory generically leads to divergent theories. They're generically asymptotic. And the first step, but in some sense the simplest step, not the deepest step of Resurgence, is to replace divergent formal series with something more general called a trans series. And I'll define that on the next slide. The idea behind a trans series, or the goal of a trans series, is that an asymptotic series doesn't contain all of the information about the function you're trying to describe. It just contains information about the function along some particular direction, say in the complex plane, and it doesn't contain the information about how to analytically continue that function throughout the complex plane. And that's sometimes physically important. We can all think of our favorite example of where that's physically relevant. On the other hand, a trans series is designed to actually contain that information. So the goal of a trans series is to really be the function. Okay, now we have to ask, to what extent is that possible or realizable or useful? But that's the goal. And the consequence of this is that perturbation theory and non-perturbative physics get mixed together. And at first sight, you think, oh, hey, that's bad, because I've just combined two difficult things and I get something more difficult. But the magic is that actually some things become simpler. And you learn some things about perturbation theory from non-perturbative physics, and you learn some things about non-perturbative physics from perturbation theory. That's interesting. Again, is it useful? Okay. There have been a lot of applications by mathematicians in differential equations, both ordinary and partial. It's been applied in various systems in fluid dynamics. It's been applied in quantum mechanics, matrix models. It's just beginning to be applied in quantum field theory and in, say, topological strings. And as I will hint, there's some sort of philosophical shift here, is that I think for many of us, when we learn about semi-classical physics or asymptotic expansions, we're sort of brainwashed to think of it as an approximation that might be useful over in this corner of the room, and only in that corner of the room. The question is, can we do more? Can we make it more useful in other regions?
Of what people in beta ansatz say asymptotic beta ansatz and full beta ansatz. So
That's a particular example.
is it example?
But it's a more general idea than that. So here's what a transseries looks like, not in its full mathematical glory, but the way it seems to show up in the cases that we've seen in quantum mechanics and field theory so far. Whoops. So instead of just having a perturbative series, you've got a triple series over three basic objects. Normal perturbative fluctuations, exponentially small things that we would call instantons, non-perturbative, tunneling effects, et cetera, and powers of logarithms that we might call quasi-zero mode contributions. So this came from a relatively abstract mathematical question of, is there a set of functions that is closed under basically all operations? It was an extremely ambitious mathematical program, sort of formalized by Ekal. And it turns out that there is. It's amazing that there's an answer to this question. And these functions are built out of three basic objects that don't mix with one another: the powers, the exponentials of 1 over g squared, and the log of g squared. And all, technically speaking, all iterations thereof. So you can have log of log of log of log of log. I've just written the simplest version at this level. Yeah.
To understand a little bit more. But then if you write this way, you assume that any singularity happens either at coupling 0 or coupling infinity. So in that form, you exclude that there are any singularities that be coupling.
As I said, this is not the most general form. Okay. And in fact, you can have functions of more than one variable. So, okay, so let me just, for the sake. Stop. You translate the problem from studying, say, perturbation theory to studying the analytic structure in the Borel plane or planes, depending on the problem. So you move the problem to somewhere where you have other tools. Okay? And then you have to ask, is that useful or not? Have you just redefined the problem, or do you learn something new? And I will show you that you actually learn something new. Okay, and first, to physicists, this just looks like something we know very well. And again, is it a relabeling or is it something new? So what do we learn? It's possible to encode analytic continuation into this. I'll show you a very trivial example soon. It looks like I've made the problem much more difficult because I now have a triple sum instead of a single sum. So that looks like a massive step in the backward direction. But it turns out that these coefficients are related to one another in very deep ways. So where did the name Resurgence come from? This is a quote from one of Ekal's books, is that resurgent functions display at each of their singular points a behavior closely related to their behavior at the origin. Loosely speaking, these functions resurrect or surge up in a slightly different guise, as it were, blah, blah, blah. So here's a picture, and if you remember anything from the talk, I'd like you to remember this picture. So the generality of the idea is very broad. Imagine you have a problem with some parameter or parameters. There may be some special points, 0, infinity, 1, -1, somewhere. These are special critical points, saddle points, singular points. And you are interested in some expansion around these points. Okay? Strong coupling, weak coupling, etc. The idea is that the fluctuations around these special points are not independent of one another. And so if you really study the fluctuations around some special point, you may be able to learn something about the fluctuations about some other special point. Depending on the context, the word special point becomes something more defined. And the surprise is that this sort of local analysis can encode a lot of information about the global structure. And in extreme cases, mathematically well studied, and again, sometimes these are useful for physics, sometimes not, but in well understood mathematical cases, it really is true that if you know everything about one particular critical point, saddle point, special point, you can reconstruct everything. Okay? Now, to a physicist, this sounds like black magic and it sounds impossible. We honestly didn't believe it. We studied it very carefully in a quantum mechanics problem, and it turned out to be true. Okay? So one of the key ideas here is Borel summation. It's just a way to control this trans series. There are other ways to control them, but this turns out to be, it seems, the most convenient. I can't explain why that's true, but it seems to be the case. Now, this is a whole subject unto itself, but and everybody's relatively familiar, I think, but let's just remind ourselves that there are two basic types of divergence that show up in physics. They're always factorial. And one case, they're alternating in sign, and in the other case, not. And the basic idea of Borel summation is to replace n factorial by its integral representation, interchange summation and integration. You then get, in this case, an integral that's completely convergent and well-defined for all positive g squared, and you define that to be the Borel sum of this asymptotic series. More properly speaking, you do the calculation properly, and you get this answer. And then if you want to study how it behaves in perturbation theory, this is the asymptotic expansion of that integral. Okay? Now, that's fine. That's well understood, and that works. It's more problematic in the case where the sign doesn't alternate. Because if the sign doesn't alternate and you go through this formal procedure, you have a pole on the Borel axis, along the positive axis, and you have to say something about what happens at that pole. Mathematically, this is an entire subject. The question for a physicist is, what physical input is relevant to tell you what to do in this situation? But whatever happens, there will be some exponentially small non-perturbative contribution coming from that pole. It'll be imaginary, and it'll be ambiguous without some further input. It'll be plus or minus I pi. Okay, so viewed from the perturbation theory world, this is very strange. You start with a perturbation series where every single term is real, every single term is positive. You generate an imaginary non-perturbative contribution, which is, at some level, ambiguous. Sometimes it's physical, as in the case of ionization or decay. Sometimes it's non-physical, and it must be cancelled. Okay? But these are the things we have to deal with. So another sketch of a trans series, neglecting the logs for now, is that you might have some perturbative expansion of some quantity, and then there's a, say, 1 instanton contribution with fluctuations around it. So that's another perturbative series, some 2 instanton level contribution with fluctuations around it, et cetera, et cetera. And there's a very important parameter called a trans series parameter, which looks just like an instanton counting parameter, but it's actually numerically very important. And I may say something more about that as I go on. If I don't get time, then I'm happy to explain that to people later. And the basic idea is that if this series is, say, non-Borel summable in the sense that it's divergent, non-alternating, factorially divergent and non-alternating, Borel summation of this generates some exponentially small piece, and if that imaginary part has no business being there, it must be cancelled by something else, and that something else must be sitting here in one of the others, okay? And that tells you that there must be relations between this and some other non-perturbative sector, okay? Just at a global level. That's the sort of thing we're looking for. All right. And this implies if you push this far, this implies very, very strong relations between the different, what we would call non-perturbative sectors. So let me give you an example of this analytic continuation business. This is an example we can all appreciate. It's very simple, and it's actually very relevant in physics. It's the gamma function, the Stirling approximation. I'll write it for the psi function because it's sums instead of products. So this is a series we all know. We all teach this when we teach quantum mechanics or statistical mechanics. It works beautifully well, but it's an asymptotic series. If you go far enough out, these coefficients start growing factorially fast. It's not me. Okay. Now, there's nothing wrong with asymptotic series. In fact, they're much better than convergent series, in fact, for actually calculating something. Now, what do we know about the gamma function? We know its functional relation, the psi function, because of what we know about the gamma function. We know this. And this series is consistent with that relation. You can check that for yourself. The coefficients are related to one another. But we also know the reflection formula, which is the analytic continuation property of the gamma function. And you can easily check that this is inconsistent with this formula. Okay? So that's what I mean. It's a sort of baby version of the statement that an asymptotic series does not contain all of the information. Okay? So you can fix this in two ways. You can actually do the Borel summation. You generate these non-perturbative terms and do all of this stuff. And you generate these exponential terms which fix the reflection formula. Or you can impose the reflection formula because it's something you know somehow. And that will force you to include these exponentially small terms. Okay? So a trans-series representation of psi has this perturbative series plus some exponentials, a whole series of exponentials, which normally we would neglect in any asymptotic analysis. And that's fine in a certain region along the real axis. But if you want to go somewhere else, it's not fine. You need those. Okay? So the idea of a trans series is to treat them together and then everything's okay. This is a very, very simple example. But let me stress that this shows up in a lot of places in quantum field theory. And I think there are a lot of cases actually in statistical mechanics where this shows up in partition functions. But there's this beautiful work by Heisenberg and Euler back in the mid-30s where they actually calculated, and here's a challenge to people, I dare anybody to try and get a formula like that in the abstract of a paper these days. Okay? Okay? And without tech. Okay? So Heisenberg and Euler actually solved it. So this is the problem of one loop effective action in a background constant electromagnetic field. Unfortunately, this is somewhat misrepresented in the few textbooks that treat this problem. They actually solved the problem non-perturbatively. Okay? They found the full non-perturbative effective action, and here it is, and it's just a Borel integral. Okay? And so the analytic structure of this complicated-looking function involving both the electric and magnetic fields has everything about the problem. It has pair production, it has these shifts of sort of Zeeman-like shifts due to a magnetic field, it has this magnetic catalysis that we heard about. It's all there. If you care to make the perturbative expansion in these one-loop diagrams with external lines, you'll be doing perturbation theory and you'll hit all of these asymptotic series. You'll do trans series, blah, 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 and you'll come back to this. Okay? This is a beautiful example of all of this story where everything's totally defined, and even these functions actually even have a name related to something called the Barnes function. And this example shows up everywhere in physics. Okay? Matrix models, all sorts of supersymmetric Chern-Simons theories, everywhere. I'm going to skip that because I'm already going too slow. Okay, the first hint of resurgence in, say, the modern era came in the context of quantum mechanics and some very beautiful work on the two paradigm cases that we use to introduce things like instantons and non-perturbative physics, which are the double well and the periodic potential. And we all know very well that there's a one instanton effect, which is the splitting here, or the band splitting here. And this goes like, say, exponential of minus some single instanton action, some number, depending on the problem, over g squared. What if you go to the two instanton level? Well, What if you look at these as perturbation theory problems? Try to study perturbation theory about one of these vacua. You discover that perturbation theory is non-Borel summable. It's factorially divergent, it's non-alternating, which tells you that if you try to do Borel summation, you'll generate an imaginary part, but these are completely stable systems, so that imaginary part has no business being there. Okay? Moreover, it's n factorial, but the coefficient is 2s, not s. So this is a two instanton effect. So you generate an imaginary part that's e to the minus 2s over g squared, not e to the minus s over g squared. Now, there's a very beautiful solution to this that was developed by Bogomolny and Zinjestana. And you can see that there's a fixed point in all of this story, which is Paris. Bogomolny ended up in Paris, Saint-Justin was in Paris, Ekal was in Paris. There's something about the food or something. I don't. So the...
Doing that, he was in Moscow.
I said he ended up there. I said it's a fixed point.
So it can be done without good food.
Okay.
Without food.
Without food. Okay. So the realization was that there was this problem with perturbation theory, this non-Borel summability of perturbation theory, but there was also a problem with the instanton gas picture, the two instanton level. Because if you start looking at instanton anti-instanton interactions, there's an instability there. Okay? And that had to be controlled in some way, and the realization was that if you control that, regulate that, and calculate, you generate again an imaginary part, which is again ambiguous, which again shouldn't be there, and moreover, it's exactly the same guy that came from perturbation theory. And in fact, they cancel one another. Okay? So the actual mechanism for doing this was realized by these guys, and various other people were involved at the time also. And this is the first hint of some form of resurgence, that at this leading non-perturbative order, relevant non-perturbative order, namely the two instanton order, these two problems in two different sectors canceled one another out. So if you treat them together, there is no problem. It's only your fault for trying to just do perturbation theory or just do non-perturbative physics. Okay, so that's quantum mechanics, and I'll say more about that later, but if we want to do something more serious in quantum field theory, then there's another source of divergence in quantum field theory, which is not just the factorial proliferation of Feynman diagrams, but the momentum dependence of Feynman diagrams in asymptotically free theories. This goes under the name of renormalons. Mithat talked a bit about this the other day. I will just say a few things. Here's the puzzle, was that if you study perturbation theory and these existence of renormalons in asymptotically free theories, you generate these imaginary non-perturbative parts, but there's a 1 over beta 0, where that's the first beta function coefficient in the exponent. Whereas if you look at the non-perturbative objects on R2, say for CPN or something like that, or in Yang-Mills on R4, the non-perturbative contributions in, say, an instanton anti-instanton type calculation would go like that, without the beta 0 factor. So this was very much discussed in the late 70s, early 80s. People thought initially that maybe this Bogomolny-Zingerstein mechanism would solve these problems, but the absence of the beta 0 said, no, it's not going to work, and people gave up. Okay. So this was one of our actually initial motivations, was to study this problem again. And the idea, starting point is very simple, is that actually in these asymptotically free theories, there's another problem with the non-perturbative, not just this instanton anti-instanton instability. There's a problem due to the scale invariance of these non-perturbative objects, these instantons. So you need to do something before you can do a controlled actual calculation, series calculation. And again, Mithat described the other day this idea of spatial compactification in a way where you drive yourself into a semi-classically calculable regime where you have some hope of actually coming out of that regime into some more interesting regime where you can probe more of the structure of the theory in a way that doesn't go through phase transitions. And the big surprise was that if you do that, at least in this CPN model, these Borel poles coming from these instanton anti-instantons and from these new non-perturbative objects, these bions, and the inferior renormalons line up, and this cancellation happens. So how does this work in practice? You have this spatial compactification with Zn twisted boundary conditions. The instantons, this is now on a small cylinder to be in this semi-classically calculable regime. These instantons, which on R2 are some localized blob, you go to this small cylinder, small radius cylinder, they fractionalize by 1 over n, and that's beta 0 in CPN minus 1. Okay, now you're in business, you can go back and you can do the instanton anti-instanton calculation, but using these basic dominant objects. Right? These are more relevant than the unfractionalized objects. You do the standard calculation for the instanton anti-instanton, and you see a generation of some imaginary non-perturbative quantity. There's a 1 over n because of the fractionalization. You can calculate the prefactor using standard techniques. And then you go and look at the corresponding calculation in perturbation theory. You do the Borel summation, and you generate exactly the same term. Okay? So this, at this point, is the most explicit demonstration in a non-trivial field theory of this resurgence cancellation at the leading order. We can talk about other examples with fermions, et cetera, but this is the basic story. We now understand this very well in other 2D sigma models. 4D is still, at this point, more complicated, but I think it's at the level of details. They're important details, but
It shouldn't be happening, right? Because we know by answer.
But then, okay, so I'll say something more about those theories. These are maybe easier field theories, maybe. This is a matter of opinion, but let me.
We don't want examples. It should work always.
Yeah. Yes. Okay, but this is this.
It works. We know the answer.
Yes. It's a
Okay, so you might say, aha, okay, well, CPN minus 1 is very interesting because we have instantons, but there are other 2D sigma models, there are other field theories where we have these problems in perturbation theory, but we don't have instantons. Okay, so this is an interesting question, and the two most accessible examples are the ON model with n bigger than 3 and the principal chiral model. They have no instanton structure, they don't have self-dual solutions, but they have these problems in perturbation theory. So what's going on? So let's describe the two situations separately.
Would be the simplest, right?
Also this. And then the work of Luciano and company.
Right.
Yeah. There it's also very explicit. So in the principal chiral model, there's no self-duality, there are no instanton equations, there are no instantons, but there are finite action, completely regular, completely smooth, completely localized solutions to the second order classical Euclidean equations of motion. They have a name, they're called harmonic maps. Karen Uhlenbeck dubbed them unitons. They're totally classified, they're quantized for different reasons from what we usually associate with instantons. They're characterized by the fact that they have negative fluctuation modes, so you might be tempted to call them unstable. That's not the right interpretation, it turns out. We studied these with twisted boundary conditions on the cylinder. They fractionalize, and these objects behave, morally speaking, in the sense of the baryon. That's their role. Okay, so they behave a little bit like these correlated instanton, anti-instanton configurations in theories with instantons, and the negative modes around these are what generate the imaginary part, and you can check this resurgence structure. Another example that's very interesting for two reasons is the ON model. Partly because, again, it has no instantons, but it has these problems in perturbation theory. The other reason it's interesting is that the beta function coefficient is not n, it's n minus 2. Okay? Now, it's easy to find finite action solutions to the second order equations. They've been studied quite seriously by mathematicians. They've studied ones with actions all, starting at the lowest possible and ranging up. These are embeddings of spheres into spheres. It's a beautiful problem in mathematics, and a lot is known. From a physics point of view, the most interesting thing is the smallest guys. These are going to give the dominant exponential contributions. And they're very easy to see. You just take an O3 instanton and you embed it into ON. It's just like putting SU2 instantons into SUN in the gauge theory, except that they're not instantons once you put them in. Okay, but they do solve the second order equations of motion. They have unstable modes. And moreover, with twisted boundary conditions, they fractionalize according to n minus 2. There's a recent paper with Mittat. This bugged us for quite a while before we sorted out all the details. The fractionalization really goes like n minus 2, not like n. So it's not just a large n effect. It's really, and there's this very nice formula in the end that the fractionalization has a nice Lie algebraic interpretation. These are the, what are these called again? These are the dual Katz labels, et cetera, et cetera. These are the fractionalized objects, and they're raised to certain powers depending on the Lie algebra. And then the sum of these guys is this dual Coxeter number, which is just the beta function for these sigma models. So it's a very general, and this behaves for reasons we don't really fully understand deeply. It behaves very much like the gauge theories. Okay? All right, so that's good. So now let me ask a more general question. Suppose, as somebody here said, somebody in the front row said, this should work always. Right? If it's going to be useful, it should work always. So let's think of having some field theory, and the idea is maybe I can say that I really can expand a partition function or a path integral into sum over all saddles with the appropriate action and with some fluctuations and maybe some quasi-zero mode contributions. And the interesting thing is that all of the theories we're interested in actually have exact non-self-dual solutions that are regular. This is not very well known to many people. I've discovered that even in Yang-Mills, there are exact non-BPS solutions. And if you want to take this seriously, the thing that's special about these non-self-dual solutions is that they're not minima. The instantons are minima of the actions, but they're saddles. But if you want to take this sort of expression seriously, you have to tell me what to do with all the saddles. It could be that they're not relevant, but you should tell me why they're not relevant. And why they're not relevant for calculating this quantity. They may be relevant for calculating that quantity. Okay? So they should be considered. Now in CPN-1, this is actually very well developed due to some beautiful work by Dunne and Zakrzewski back in 1980 and thereabouts, which we studied again with fractionalization, is that all of the finite action non-BPS solutions are classified. And the construction is extremely simple. You take the representation that Misha was describing before in terms of this holomorphic vector, call that V, take its holomorphic derivative, fine, so that's some other holomorphic vector, but then you project it, right? You project it against V dagger dV, okay? That's no longer holomorphic. But it turns out it solves the second order equations. And you can just check. And you can prove that all of the guys generated this way are the only ones that give you finite action. But they're completely classified. Okay? At the
boundary conditions when
it doesn't turn out to matter. So you can do this on S2, you can do it on R2, you can all of that's taken care of.
in all cases you have solutions.
No problems. Okay? Now these were studied by mathematical physicists, and there's lots of beautiful stuff, but at that time they had no idea what they meant physically. We now know the role of these guys, the reason they exist, presumably, is what's special about them is that they have also these negative fluctuation modes. So if you're going to take this sort of formula seriously, there will be imaginary contributions from these saddle points, and they shouldn't be there, right? If you're calculating some real quantity. So if anything's going to work with this formula, there must be these sorts of cancellations. And then that tells you that there must be relations between different non-perturbative sectors. Okay? It's just unavoidable if you're going to think in this language. It must work. Okay? Now, even in Yang-Mills, there are non-BPS, non-self-dual, finite action, completely regular solutions. So again, if you're going to think in this language, you have to understand what
you have written there.
even for SU2. It's proven by Karen Uhlenbeck and by the Sibners that these exist. This is based on work by Taubes on monopoles. It's very easy in SU3 and above to write ansatzes where you can construct these. The tour de force of these people is to prove rigorously existence in SU2. Okay?
Is it still on the cylinder, or it's?
No. This is an R4 or S4.
S4. I thought question to S4 actually Kallenberg proved that there was not.
No.
Starts from S.
No.
Are these things point-like or line-like?
They're lumps.
They're lumps, just lumps.
Yep, they're completely smooth, completely regular, nothing sick about them that would make you say, oh, I don't care about those guys. Okay? They're not very explicit in the SU2 case. That's one of the problems. Okay?
So tau is at this example, right? This default amount.
Yeah. So that you upgrade that a dimension and you get these things first. Anyway,
What roughly the reaction is? These lumps, which action? I mean, the size of the action.
one. One in the appropriate units. They
Compared to the instanton action.
2 times instant.
2 times the instant.
2 times instant.
Okay, so let me just state, this is an open problem. even though the existence is known and in CPN they're classified, essentially nothing is known about the fluctuations. Okay? You just lose holomorphicity, you lose twistor structure. It's a much more difficult problem. Okay? And I think I should say this to this community, it would be extremely beautiful if some numerical information could come from the lattice to give some guidance about the studies of zero modes, fluctuations, because it's a really difficult analytic problem. But the lattice is now so powerful at studying these sorts of relations that maybe we can learn something.
But they have moduli space or they are right?
Yeah.
They have both modular and quasi-moduli space.
Okay, I have to continue. Sorry.
The measure is non-zero.
Yeah.
The measure to pass.
Okay, I have to proceed. So there's another more developed story. Actually, I think in my mind the first really beautiful paper in this sort of modern era related to field theory was this work by Mourinho and Schiappa and Weiss studying how this works in topological strings and matrix models. It's a fantastic paper, and there's been a whole series of works by Mourinho and collaborators and by Schiappa and collaborators developing this in topological strings and in matrix models. We had this workshop here back in April. There have been a lot of recent developments, and it's very well understood, and it's an extremely beautiful story. Let me mention it. It's maybe not the closest interest to most people in this audience, but it's extremely nice. And there's actually some very recent work that was presented at Lattice showing that complex instantons really exist here. So let me now talk a little bit about what's going on here. Why should this be working? Is this just magic? So I really want to make sense of this type of picture. To what extent could it possibly be true that perturbation theory contains or encodes all the information about non-perturbative cycles? It sounds like it's impossible. Okay? Could it be true, or could it just be some special thing for some differential equations? So there's this other fact that is very, very unknown amongst physicists, is that we motivate all of what we do from non-perturbative physics from these simple contour integrals in one dimension. We do the steepest descent analysis, but we stop at the Gaussian level. So you can just ask the question, what happens if you don't stop at the Gaussian level? What happens if you just keep everything? And this was studied, this is quite recent, okay? By Berry and Howells in context of something they call hyperasymptotics, but that's not important. The important thing is the result here. Imagine you have some ordinary contour integral going through one of the saddle points, critical points of this function f. Suppose it has many different critical points. So there are different saddles. You can write through these different critical points. And here's the usual approximation in red. There's the contribution from the value of f at the saddle point. There's the fluctuations. And then there's all the stuff that we ignore. Okay? So this is a series in G squared with some coefficients. Now the question is there anything interesting going on in those coefficients in that series? And the answer is yes. You can prove by just manipulation of contours, elementary complex analysis, with relatively mild constraints on the function f, that there's an absolutely explicit integral relation between the fluctuations around saddle point n and saddle point m, where there's a technical definition of which guys are connected to one another according to whether they can be related by steepest descent paths. And this is absolutely exact. And why is it useful? It's useful, and this capital FNM is the difference of the actions at these two saddles. And it's interesting because I can now expand this in small g squared, and so I get an expression for this series around saddle point n in terms of the series around saddle point m. And if you do all the integrals, you learn that the coefficients, so this is labeling the saddle point, this is the order of the expansion in g squared, goes factorially, we know that, that's generic. And the power is the difference of the actions, that's conceivable. There are some minor signs depending if you're going this way or this way on the contour. But the interesting thing is that the coefficients, the overall coefficient, is the leading coefficient around saddle point m. Okay? And this is just an absolutely basic general result about steepest descent. And you can look at the subleading orders, and they also involve the coefficient. So let's look at an example. Here's, say, a zero-dimensional partition function of a periodic potential. It's just an ordinary integral. It's just a Bessel function. We know everything about this integral. It has two saddle points, one at the origin and one at pi over 2. I can look at the expansions around these 2 points. The integrals are all doable. Here are the coefficients around the, say, the vacuum, the 0. They're just some gamma functions. I expand them at large order, leading factorial, and then there are some numbers here for the subleading term. They're just some numbers that come from expanding the gamma functions. Then you go do the other integral around the other saddle point. Okay? And they're just the same numbers. Okay? All right? And this is absolutely general property of steepest descent expansions, which you see and appreciate if you go beyond the Gaussian approximate. Now, the big question is, could something like this possibly work for path integrals? Well, of course, you can now go look up the literature and you discover that even doing this in 2 dimensions is spectacularly complicated. So the natural thing to do is go directly to infinite dimensions and just do a calculation. And you do a calculation and you discover, so here I'm now doing quantum mechanics, so this is not field theory, but it's a path integral calculation. And here's the subleading corrections to the leading factorial growth that I told you about in perturbation theory. You can calculate many of these numbers, and they're numbers. And then you go look and you do a difficult calculation, which is the fluctuations around the instanton, anti-instanton. That's the nearest sector that has the same quantum numbers as the vacuum. And you discover after a lot of difficult work that you just wasted a lot of time, that the numbers are the same. And you can do this in the double well, and you get all these very strange looking numbers, and they're just the same. Okay? So this is telling you something. It's not clear how general the something is, but it's telling you something surprising. And it turns out it's even more interesting than that. So let's look again at these generic problems. So here, I'm not going to go into detail. There's a couple of papers with Mittat a few years ago. Just do perturbation theory in these. You generate some trend series. That's what's contained in this paper. It's very simple to understand where this weird trend series comes from. But there was a lot of work by Zingestin and by Genschur in the mid-2000s, and they came up with a conjecture that, in fact, you can generate the entire trend series from 2 functions. So think of this picture of these special points. They claim that you can generate everything if you know the fluctuations around the trivial vacuum, so that's perturbation theory, and if you know the fluctuations around the single instanton. Okay, so there's a beautiful, extremely deep result, conjecture, whatever you want to call it, that you can generate everything else from these 2. Okay? So we were trying to understand this in the language of this very ambitious Resurgence program, and we noticed something stunning, which is that, in fact, if you give me this, namely perturbation theory, I can write down this in 1 line. Okay? Okay, so don't worry the details of the formula. There's a formula. And it's constructive. If you want 25 orders of the fluctuations around any non-perturbative sector, all you have to do is give me 10 minutes and 25 orders of perturbation theory. Okay? And if you want 50 orders, you just give me 50 orders. Right? So it's completely constructive.
Define service. So this is first example when we can.
Okay, but there's a difference between believing and seeing. So let me show you in the context, let me just finish this. Let me show in the context of this conference some beautiful recent work by Edward and Sasha and Escobar Rios. They went back and they studied the double well. I'm showing the double well result, but also they've done now the Sine-Gordon case. They did a heroic calculation, which was to do, as you would do in field theory, the fluctuation calculation to 3-loop order around the instanton sector. So there are zillions of diagrams which you can't even see because the projector isn't very good. But trust me, there are many diagrams. They're very difficult calculations. Not all of them can be done analytically. Some of them had to be done numerically. And these are the numbers that they calculated. Okay, this 6 or 7 digits. Given our formula relating perturbation theory and this instanton sector, we can write down for any n, not just the vacuum level, to this order. And this number, this weird number, agrees with this number to that many digits. Okay? And same thing, there's a corresponding formula in the periodic potential case. So this is telling you several things. First of all, it's true. But I think more importantly, it's telling you that there must be a different, possibly simpler way to do the field theory fluctuation calculation in the instanton sector. Okay? It should not be necessary to calculate these 30 different 3-loop Feynman diagrams, add them all up, and look at all the cancellations and get a number that's numerically a rational number, but is this rational number. Okay? An extremely beautiful piece of work. And I think this is the sort of thing of seeing rather than just believing. Yeah.
In case of the work that you said about Marino and so on, we know that the fixed by duality.
Of course.
So
So
in that case, we have analog of gamma function.
yeah, absolutely.
In this case, we don't.
Right.
Yes.
Right. This is deeper, I think.
So
I'll tell you later offline why this is working. That's another talk. Okay, so it really seems to be true that at least in these cases, which remember are the starting point for all of our discussions of non-perturbative physics, okay, even in gauge theories, the periodic potential and the double well potential. In these cases, there's this surprising, first of all, it's surprising that you can find anything new about these systems, but it's surprising that this ambitious idea that everything is encoded in the perturbative sector really seems to be true. Okay. All right, so let's see, where does this lead us? This leads us to thinking that actually maybe we should take this sort of formula really seriously. And if we take this sort of formula really seriously, it means that we should have our eyes open to the possibility of complex saddle points, because that's generically what happens for integrals. We all know that real integrals can be dominated by saddles off the real line. That's a very general phenomenon, and that's in fact what Stokes discovered. This is what Stokes was struggling to understand in the old days. And in functional language, that's called thimbles. Thimble is just a fancy word for functional steepest descent contours. But let me just say why this could be extremely interesting for QCD. Imagine what's special about a steepest descent contour. What's special about a steepest descent contour is that the imaginary part of the action is fixed. That's the definition of a steepest descent contour. So if you could make practically useful sense of the concept of an infinite dimensional steepest descent contour, okay, which has not been done yet, but if you could make practical, concrete sense of that, you would have the opportunity, for example, in a problem with the sine problem, you could deform the contour, whatever that means, in your functional integral, and have the imaginary part fixed, which you take outside, and you're left with something that is amenable to semi-classical analysis, Monte Carlo, whatever you want, to high precision, okay? So that's the goal. Nobody's achieved it yet, but that's the goal. And it's a very tantalizing question, and the fact of the matter is, it has worked at the level of some quantum mechanics problems. We can show you cases where these complex saddles are absolutely relevant, and I'm even going to show you some experimental data in a few slides if people let me get there. That this really works, okay? Now, to do it for QCD is beyond anybody's capability at the moment, and there are various techniques. We've heard about gradient flow. There's complex Langevin. There's a lot of confusion at the moment, but I think it's a very exciting idea and something to be explored. And things are developing quickly in the last year or so.
Holomorphicity of the action? The top line right there?
So the first step in the idea is to start with something that's real and just upgrade everything to complex. So of course there's some underlying assumption about some level of analyticity, but the holomorphicity just follows immediately from complexification.
When you have dynamical fermions and you have a fermion that's...
There are many details that are not understood, and it's clear that there are details, especially when you include fermions. Okay. But the idea, I hope people can appreciate the idea. That's the important thing. Okay. All right, so we've heard all about this. The thing that Resurgence can add to this story is that if you are able to do this, there are actually relations between this thimble and that thimble. They're not independent of one another. And that can be useful. All right, so I'm going to skip that. So yeah, let me show you, just for the hell of it, let me show you some experiments. These complex saddles really exist. You can show, and they're experiments. So think of the Schwinger effect, particle production in QED in an electric field. Okay?
He had a
Yeah.
paper there which had a
So Heisenberg derived everything before everybody else. It was actually Euler's PhD thesis, so Euler should get the credit. Okay? Okay. So.
But some classical.
Come on. Let me. No. Okay, so if you think of doing this, you can't do it with a capacitor. You have to think of it doing it with a laser. So you have to think of something closer to a laser pulse with some Gaussian envelope, some frequency, and so there's something called the carrier phase, which is the offset between the peak of the carrier wave and the oscillating thing underneath. And it's known to atomic physicists that ionization in such a laser field is spectacularly sensitive to phi. And you have experts on that here at Stony Brook. And so we studied this numerically in the Schwinger effect, particle production from vacuum in this type of field. And it again was spectacularly sensitive to phi. This is the momentum distribution of the particles produced along the direction of the longitudinally polarized electric field. And phi equals 0, you just have some sort of regular Gaussian distribution, and here you have something like this. So why is this happening? This is happening because for this type of field, you look at the complex saddle points, and there's one complex conjugate pair which dominates everything. Whereas if it's pi over 2 out of phase between this and this, you have two pairs of complex conjugate points, and the interference between them gives you these momentum oscillations. You can see this explicitly in the world line representation of the effect of action, and it translates immediately into complex saddle points of this action. And you can see now why it's complex. As soon as you have a background gauge field, the instanton actions involve a first time derivative. You're stuck with complex solutions. Right? Try and do the problem of tunneling in the presence of a magnetic field in non-relativistic quantum mechanics, you'll see exactly the same problem. So we did all this, and you can see that these interference effects are directly related to the existence of these complex saddle points in this functional integral. There are even experiments. So these are experiments in the analog in atomic ionization. And you can see at the pi over 2, this is the energy, not the momentum, in one direction. And this thing here is exactly this thing here. Okay? The red and the black is in one direction or the other. I can't remember which is which. And when it's out of phase, you see this interference effect. There are even recent experiments with tunnel junctions in condensed matter systems. It's exactly the same physics. And these oscillations here are exactly the oscillations shown in that. And you can trace them exactly to these complex instantons. Okay? So it's not some esoteric thing. It's actually measurable. And we should take this seriously in field theory. So let me finish with one recent example that's in progress. This is work with Gökçe, who's here somewhere, I guess, hiding there. So this was inspired by a recent paper that's quite interesting by Heller and Sperlinski. So resurgence is a completely generic phenomenon for differential equations. So there are certain problems in physics that you can just reduce to some interesting coupled differential equations. And hydrodynamics is a classic example of interesting, complicated coupled differential equations. Okay? And it's of relevance to this sort of community because of its relevance to, say, heavy ion collisions. So just to see an example of how this can work, let's take the simplest possible example. You take conformal hydrodynamics, so everything's reduced just to the, say, the energy density, and you take this boost invariant limit, so everything's just a function of some proper time variable. So we've taken the complicated differential equations and reduced them to a complicated ordinary differential equation, just to get a handle and see how this works. And what you see is you get, so E is the energy density, tau is the proper time, phi is related to some viscosity effects. You can combine these two and get a single, horribly nonlinear differential equation for the energy density, and then you can express these things. This guy's something that shows up in second order hydro related to some time relaxation effects. This is viscosity, and this is some other type of viscosity that shows up in second order hydro. And then normally what people do is they make large proper time expansions where you expect to be in this hydrodynamic regime. And the observation of Heller and Spolinsky is that these types of expansions are clearly asymptotic, and you should do some sort of resummation. And if you do some sort of resummation on these, you see the non-hydro modes. These exponentially suppressed things, these are beyond normal hydrodynamics, and these, in the gravitational language, are the quasi-normal modes. And the point is, you can see these absolutely staring you in the face if you just look at the perturbative series, okay? Which is normal hydro, but you look at it at high orders. So how does this work? This type of expansion, which is what people typically do, and you're in the hydrodynamic regime, should be upgraded to a trans-series, and you can project all these numbers and all these fluctuations. So let me just show you a simple example, is that here are the coefficients of this expansion around the perturbative hydro expansion. The thing we're calculating is real, so the fact that this thing is non-alternating, factorially divergent, means that you generate imaginary parts. They must be cancelled. The imaginary parts of them must be cancelled. That tells you that those imaginary parts must be related to the fluctuations around, this sector. Otherwise, and we're just talking about a differential equation here, nothing complicated. So this must work. So you can actually make this very precise, and there's extremely beautiful work by Aniceto and Schiappa, who applied this concept of reality and translated into completely general cancellation relations between different orders. You can now just look this up. It's like a textbook. And so here is what you find. You find that there's a factorial divergence with some coefficient. And these you can calculate, these numbers, beta and s, you can calculate just in one line by doing a simple fluctuation calculation. And the idea is that the coefficients at large order around the hydro expansion, the coefficients are fixed by the coefficients around the next order in this trans-series expansion, okay? So it's just a differential equation. You plug in a trans-series, you generate recursion formulas, you can Mathematica code, even I can write a Mathematica code that can generate 10,000 terms in, that long. So there's a lot of data, you can check this. Here are the subleading corrections, and this is what happens. This is the ratio of what you predict to what you generate, and here's 1. Here's 500, we have 10,000 orders, but it's no point after a while. Here's, if you just take the leading term, it's clearly going to the right limit. But if you include, say, these first 3 terms, it's absolutely flat at order 10. Right? It's absolutely clear that this is the right relation, and you can actually calculate numerically the Borel plane structure of this expansion. And we did this up to 10 instanton level, and it just works, period. It just simply works, okay? Now why, so that's a mathematical statement. The question is physically, why is this interesting? This is interesting because you can actually identify things beyond what we normally think of in hydro from hydro, okay? And this means now, this is this very simple case of boost invariant context. If you now treat more complicated cases, say in this ADS approach, there are these gravitational metric coefficients that don't just depend on tau, they also depend on some other variable z. You now have partial differential equations to deal with. Well, this trans-series structure is also understood for some partial differential equations. It's not as well understood, but this is clearly a hint that this should be taken into account and studied in these cases.
Hydro is suspected physical ground. It is at core. The other one which you mentioned is much lower.
And I have, I think, 1 minute probably. So let me just show a picture. Okay. So let me just end with a picture because and I want to make a point here, because I think there's a certain level of misunderstanding amongst people. So we've heard in many, many, many talks that a generic problem in physics is to understand the relation between strong coupling and weak coupling, possibly by some dualities, and try and understand that in this sector, weak coupling or strong coupling, these monopoles are relevant, or these dions are relevant, or these electric degrees are relevant, or these magnetic degrees are relevant. If you believe any of this story about resurgence, it should at least in principle be possible to describe the transitions between these regions and possibly the dualities between these regions. Let me show you a classical problem, which is the Matthew equation, periodic potential. I'm drawing here the band structure. So this is the energy, the eigenvalue, as a function of h bar. So 1 over h bar is like the height of the potential, or 1 over h bar squared. I don't remember which. So when you're in the potential, which is between -1 and 1, you have these very narrow bands. They're exponentially narrow. And we know that the narrowness of these bands is related to instantons, which are tunneling between the wells. Okay? So that has all been upgraded to trans series. It's all understood. This is where we found this formula relating perturbation theory. So that's good. Okay? But I cheated you a little bit in that discussion because I was talking about bands that were exponentially narrow, and I was talking about this region down here. But it's not the only region. There's a region up here, okay, which is where the level number, or the band label number, is much bigger than 1 over h bar. Or in our language, it's where this 't Hooft coupling is large. Okay? So actually, what we're talking about is a trans series in 2 variables, n and h bar. And I only told you about the region where n was much less than 1 over h bar. Okay? So it turns out you can actually do this. And it's physically interesting because, believe it or not, this spectrum is in absolutely one-to-one correspondence to a certain very important quantity in certain supersymmetric gauge theories related to their low energy behaviors. Absolutely explicit one-to-one correspondence. There's a dictionary mapping these things to one another. And in that language, this is called the electric sector, this is the magnetic sector, this is the dionic sector. There are dualities between them, but those are sort of special things because these are nicely supersymmetric guys. There's a more generic question. How does it happen that a system that we describe physically in solid state language via localized atomic levels inside bands, this is tight binding approximation, tight binding degrees of freedom, and we can describe it using those degrees of freedom, how does that relate to a system up here where we solve it using completely different degrees of freedom? Plane waves. Okay? So how do those two guys fit together? And how do they fit together in the region near the top of the barrier where the bands are not exponentially narrow and where the gaps are not exponentially narrow, but they're of the same order and they're of order 1? So the words are that as you go up in the 't Hooft coupling, you need more and more instantons. The instantons condense, whatever that means. And then they mutate into, up here, something's governed by complex instantons. There's this beautiful work back in the old days in solid state physics. As far as I'm aware, the first work was by Dikne, some Russian solid state physicist, to show that everybody knows that the width of this band is given by an instanton action, but the width of those gaps is given by a complex instanton action, because up there above the barrier there are no real turning points, but there are complex turning points. But you just calculate exactly the same thing, exactly the same formula, and that gives you the width of the gap. But they're different objects. They're complex instantons up here, they're real instantons down here. Here you need both. And moreover, there's a gauge theory translation of all this. And the point is, you can do this. If you study the series here, they're all divergent, all this Borel summation applies. Up here, the series are all convergent. So how on earth does a divergent series turn into a convergent series? And again, this is classical mathematics. You can look up the formulas in the divergent region. You can look them up in a book. You can look up the formulas in the convergent region. These are convergent, these are divergent. They must be the same thing. So believe it or not, we found something interesting about this. So you can rewrite in the divergent region as a trans series. Here's perturbation theory. Here's the one instanton coefficient. There's the fluctuations. These guys are related to these guys, etc. That's the story I've been telling you. You can take these complicated looking expressions, which are convergent, and you can rewrite them in a way where you have a finite series, plus or minus, not an exponential, but a power, times another finite series, because they're convergent, and plus higher powers with other series. So you've rewritten it to look like a trans series, even though these are convergent, and in fact they're finite for a given n. And the magic is, these numbers here are related to those numbers there in the same way that these numbers are related to these numbers. Okay? And it's mind-blowing that this problem has been studied for 1,000 years or whatever it is, 150 years, and nobody ever bothered to rewrite these expressions in this form. Okay? And you can do this in now more detail. You can study it in the region near the top of the barrier, and you see with your eyes how this instanton condensation effect happens. You really see. Okay? So this is a simple problem. This is quantum mechanics. But this is what we hope may be possible in some field theory. So I really have to stop. So let me just show this and stop. Thank you.
Gerald, results are fantastic. But you said several times that there is a hope that by the resurgence you would keep out all non-perturbative physics. And here, you see, then now I formulate my question. Imagine that you have Lagrangian and different parts have different types of symmetry.
I can preempt your question. Clearly, all is too much.
Okay. Then I'm
Okay. The question is, can you?
Yeah.
I think a more relevant question is, can you find any?
Yeah. This you already showed.
Okay. No, all is too much.
General questions.
Okay, I have a question. So you talk about this expansion in one instance or another instance, but there are 9 set of, let's say, that they think about the background field, where you can also do concentration and do the series of perturbative expansion.
I showed you the
Similar there.
Yeah, so the Euler-Heisenberg case is the classic example. Background field. You can do it with gravitational backgrounds, electromagnetic backgrounds, QCD.
Even if there are not saddle points, somehow it's still related. But
No, there are saddle points in those cases, clearly. You re-express the background field problem in this world line language, or world sheet language if you're in more complicated theory, and there are saddle points.
Okay, guys, last question, please, and we need to, otherwise we don't have coffee break.
Have coffee.
Please.
So, given how useful Feynman diagrams are for the normal series expansions that we make, do you think there's some scope for a diagrammatic scope to trans series?
Yes.
Yes.
No, I mean yes, but the flip side of that is that there will be some things you calculate with Feynman diagrams where you will discover that that was the wrong way to calculate.
Right.
Okay, so it's backwards and forwards. So one very clear example is you go to the operator product expansion for some theories that have some degrees of supersymmetry or some special symmetries, which then tell you something non-perturbatively. So the operator product expansion is also a mixture of non-perturbative condensate type terms and fluctuations, and they're related to one another in this sort of way. Okay? Now you can view this in 2 directions. You can say, I learned something about perturbative series, Feynman diagrams, and that tells me something about condensates. But turn the argument around. Suppose you know for some reason, supersymmetries, global symmetries, whatever, that some condensate is 0. And really 0, not just sort of 0, but 0. If you believe that there is this resurgent structure within E, that translates into some very non-trivial statement about some perturbative set, which is extremely non-obvious to prove, even to study, using Feynman diagrams. Okay? And that's an example of, but there are many other examples where So I think the message is that you should keep an open mind and consider these two things together.
I want to add about our particular example. So there are free loop diagrams around vacuum and free loop diagrams around instantons. And basically diagrams are the same, just formulas are different. So there are many terms we were hoping we will see some tendency that this diagram is related to this diagram. Resurgence relation is a relation about the sum. We couldn't find any relation between diagrams. Yeah? It really some random numbers and then the sums are related, but not, we have no idea whether individual diagrams have any connection.
Right, so
That's kind of.
So I think Sasha will talk about this there. So
Okay. We have a break and we go only 10 minutes till 11:30.